Okay, so today's second question is 438. Find all anagram in a string. So anagram is basically a string with its characters shuffled around, randomly shuffled around. Given a string S and a non-empty string P, what we need to do is find the starting indices of P's anagrams in S. So I guess S should be at least longer than P, otherwise we wouldn't be find a permutation of P in S. The string consists of lowercase English letters only, so that we don't need to worry about some weird case letters, I guess. And the length of both strings S and P will be reasonably short. The orders of the output doesn't matter, as long as they are the correct starting indices. The example here we have CBA, EBAB, ACD. The string P is ABC, so we need to find ABC, ACB, BAC, BCAC, ABC, BA in S and return their starting index. So that's CBA starting with index 0 and BAC starting with index 6. The second example we have ABAB, the string P is AB. So anytime that we see AB or BA, they are all valid anagram of AB here. So there are three such substrings. The indices are 0, 1, and 2. So really quick and easy solution is to create all the permutations of P and just iterating over S once, checking the substrings of the same size, same length as P, the length of P, and checking whether that substring is in the set of permutations. If it's in there, we just append the starting indices to the output array. After we doing this one pass, we will be done. The problem is that the checking is actually fine. It's a linear, and the lookups is going to be constant. But the problem is going to be creating all the permutations for P. So I think that's a factorial in terms of time and space complexity. Yeah, so that's not the idea if the length of P is large. If we somehow know that P is relatively short, like a 3, 4, I guess it's doable and it will be fast. But since there's no guarantee how long P is, we only know that it's not larger than this 20,000 something. Yeah. So it could be very time consuming to creating all the permutations. But that's the valid solution, at least valid first solution. Then we begin to realize that to actually determine whether CBA is a permutation of ABC, all we need to do is basically looking at the frequency count for each characters. So we have 1A, 1B, 1C in the requirements here, and CBA has 1C, 1B, 1A. So they match each other. Then it must be a permutation of P, the string P here. So this will reduce the so instead of checking whether this substring is in the set of all the permutations, we compare the frequency count of the characters with the required frequency count. So the checking will become this, and we no longer need to create a permutation of P. So just in terms of this solution, in terms of time and space complexity, we will need to store the frequency count for the characters in P and the frequency count of the substrings in S. So these is since we are only working with lowercase English letters, it's maximum to be order of 26. So we can argue that the space is for these two hash maps is going to be constant. And the time complexity is order of the length of P to create that hash map for P, and for S it's a little bit complicated. So if at each location we create a frequency count from scratch, then because we have an S location, length of S location to go through, and for each of those locations we are creating a hash map frequency count out of MP, length of P, length substrings from there. So it will be these two lengths multiplied together. But that will be doing a lot of redundant work, because when we look at the CBA and BAE, if we do that, we calculated the frequency for B and A twice, once in each window. So we don't actually need to do this. All we have to do is to maintain a frequency count window, and once we move to the next location, we try to decrement the exiting character and increment the frequency count for the new entering character. And yet another optimization we can do is to only keep track of the frequency count of the characters that's required, that's in P, because anything that's not in P, we don't need to worry about that frequency count. So with all this, the time complexity for the moving window frequency count checking matching method is going to be linear with respect to these two strings lengths added up together, and the space complexity is constant. So with that analysis, let's code this question now. So the first thing we do is to handle the edge case where the string S is actually shorter than P. So in that case, we couldn't find any permutation of P in S. In that case, we return an empty list with no indices in it. So the length of P is something that we grab here, so make the code a bit cleaner. The required frequency count is we create this out of the string P. So with the counter, we're basically just counting the number of occurrence for each characters in P. And we get our first window by the very first substring in S, that's the same length as P. So it's another counter here. But the content in here is actually the characters that appears in P. So because anything that's not in P, we don't need to worry about. So that's the first n characters in S, as long as that it's a required character. Maybe we'll do this. Do the initialization early on. Then we do a very simple, do our initial comparison whether these two frequency count is actually the same. If that's the case, we append 0 to the solution here. No. So much typo today. After the very initial window, we just try to enumerate the characters after that one by one and trying to update the window. So this character here is the entering one, and the exiting one is I minus n. Again, we do this checking here so that if it's like characters like E, it's not in ABC, we don't need to do anything to the window. Subtract Si minus n. The comparison, we just copy this. Jeez, my mouse is drifting today. The location is going to be I minus m plus 1. So looking at here, yeah, so the location we're gonna get this second 6 here is gonna be 7 and 8, actually 8. So 8 minus 3 and plus 1 is 6. Yeah, so that's the that's a little bit mask here to make sure that we get the starting index rather than the ending index. So this will be the code for this question. Let me see if we have any problems. The name, the required frequency, the initial window, that's the characters that's in frequency, the first n letters, that's in the frequency, required frequency. And then we try to expand the window, not re-expand, we try to shift the window one location at a time. We update the window with the incoming one and try to decrement the frequency for the exiting character. After we updating the window, we do this checking again and make sure that we actually add the starting index for that window if it's an anagram for the required P here. In the end, we return the solution. It looks good to me. So yeah, let's try to submit this. Okay, it's working, but a little bit slow. Yeah. So, but based on the analysis, this should be linear in time and constant in space.